Ability to effectively work with images is a part of what an iOS developer should know. But how well do we really understand what an image is, in what format it exists, how it's displayed and processed, and finally, how to make an image usage in our applications more efficient? So, who is this video for? For anyone. If all you know is how to display an image using your image view, you will find some foundational knowledge here. If you are an experienced developer and understand concepts like alpha blending, pre-multiplied alpha or gamma correction, well, probably you know everything I will discuss in this video and even more. However, you might still find a few practices for working with images that you can adapt in your work. But before we dive in, let's remember the main characteristic of the screen. The first one, resolution, refers to how many pixels we have on a given screen. It's defined by how many pixels we have on the horizontal axis, the width, by the quantity of pixels on the vertical axis, the height. So simple. Second one, density. The density of a screen is relation between the physical size and resolution, normally measured by ppi or pixels per inch. It's a quantity of dots or pixels that fits into an inch of that screen. The higher the density, the better the quality of the image, because with more pixels the image can be more detailed. As you can see, iPhone 6 has 326 ppi and resolution 750 by 1334 pixels. Don't worry about points, we will talk a little later. Alright, now about the formats. They are vector and raster images. Let's start from the raster or bitmap. It's just a matrix of rows and columns where each intersection is painted with a color. Turning the bits into bytes, let us represent a wide palette of colors for each pixel. Each pixel represents a number, and by applying a palette, which maps each number to a specific color, we can produce a colored bitmap. The higher the number, the most colorful the image can be. Since raster images are pixels-based, they are resolution-dependent. The number of pixels that make up an image, as well as how many of those pixels are displayed per inch. Both determine the quality of the image. As you might have guessed, the more pixels in the image and the higher the resolution is, the higher quality the image will be. For example, if we scale up a raster image without changing resolution, it will lose quality and look blurry or pixelated. This is because we are stretching the pixels over a large area, making them look less sharp. Different algorithms are used to resize the image properly. For example, nearest neighbor interpolation. Bitmaps are perfect for your phone screen. Remember that a raster image consists of pixels. This is one-in-one representation of a computer or phone display. Display controller simply takes a pixel and places it in its place on the screen. Now about the vector images. Vector graphics describe images using straight and curved lines, called surprise vectors, as well as parameters that describe their colors and positions. Vector just mathematical commands to draw geometry. You remember that the screen is made up of a grid of pixels. This is why we can easily display a raster image on it. But how do we display our vector images? Yes, they are vector display too, but generally we don't use them. Before displaying on raster screens, the vector goes through a mandatory stage, rasterization. Rasterization is a stage in the rendering pipeline that, using some algorithms, converts a vector image into a raster one. There is also the reverse process, vectorization, but this is much more complicated. You definitely won't be able to vectorize an image one-to-one. However, you can use services online or even ask ChatGPT to make vector images from the raster one. And once again, difference between vector and raster on this picture. The name Retina display was introduced by Apple in the release of iPhone 4. The screen is called Retina because PPI of the device was so high that the retina or the human eye didn't have to distinguish pixels of the screen. Technically, such screen display twice as many pixels in height and width at the same physical size. The name Retina belongs to Apple, so other companies use high DPI instead or no name at all. iPhone 3 had a 3.5 inch diagonal and resolution of 480 by 320 pixels, which correspond to 163 ppi. iPhone 4 also had a 3.5 inch diagonal and a resolution of 960 by 640 pixels, which correspond to 326 ppi. Same size, but iPhone 4 has more pixels. I mentioned that before, that such display twice as many pixels in height and width at the same physical size. So, where the first iPhone has 1 pixel, the fourth has 4. 1 normal pixel equals 4 Retina pixels, 4 times as many pixels, and the 6S Plus has 9 times more pixels instead of 1. iPhone newer than the 6S Plus used 3x. More pixels in the same square inch means you need bigger images. And Apple has started to require apps to be compatible with the Retina display. Otherwise, they will be rejected during the app review process. So, you have to provide 3 versions of every image for your app. But don't worry that unnecessary pictures of unused sizes will take up space. App slicing will help with it. It's a server-side feature provided by App Store Engine. When the user downloads your app, he receives a cut-off version of that original package with the image that doesn't fit the device screen density are removed. You can ask, can I technically use just 3x pictures? If you ship assets with a higher scale factor than the target device, they will be displayed fine, but downscaling them in real time has performance cost. They take longer to upload to the GPU, they take GPU time to render, so if you have only 3x images, you can downscale it on Photoshop yourself. I promised to tell you about the points. Let's do it now. In order to generalize the work in 3 densities, the concept of points is introduced. A point in 1x consists of 1 pixel. A point in 2x consists of 4. A point on screen with 3x out of 9. You can meet points when you set up an after layout for your views. It seems that everything is simple, but let's fix the information on example anyway. We have a WhatsApp logo 36 by 36 if we want to embed this image in our application. How can we support the display for Retina? We can't use the same picture for all type of screen. What happens if we want to display this logo at 2x and 3x screens? Without resizing, the picture will appear smaller. You can resize it in runtime, but this is unnecessary work, and as we remember, the picture quality will be worse than the original. Therefore, we leave it as it is for 1x, for 2x we double the numbers of pixels for horizontal and vertical axis, and triple for 3x. This will be the case if we put the resulting images on the 1x screen. We place 3 versions of that logo in our bundle, and then a corresponding logo will be taken for each of the screens, the rest will be cut off. Now we are moving on to more practical things. When to use a vector and when to use a raster. Vectors are ideal for storing and working with 2-dimensional images composed of line-based elements such as lines and polygons, or simply geometrical objects such as text. Raster files are better for complex, highly detailed and true color images and graphics, such as photographs. Raster display a wider array of colors and show finer light and shading than vectors do. You can also edit color pixel by pixel. Once again, the difference stands in vector images describing what they want to draw, and the raster image describing the color of each pixel, due to which they are heavier in size. Bitmaps are best for representing pictures and highly detailed images. Vector best for simple shapes. Icons, for example, that needs to be scaled at runtime. Now let's figure out which format is better to use for vectors and for rasters. Let's start from the little overview. PNG Can have an alpha channel is how transparent each pixel is. Simplified, it supports transparent backgrounds. Have lossless compression. It means that the initial data could be perfectly restored from the compressed version. Pixel perfect image. JPEG can have an alpha channel and lossy compression. PNG and JPEG are both binary formats. JPEG is a lossy compression. Refers to a method of compressing digital data where a portion of the source file's data is intentionally discarded. When it's done correctly, we don't see any noticeable difference between an uncompressed image and its JPEG version. However, repeating this compression over and over again will accumulate this little intentional mistake JPEG makes, and the difference may become noticeable, like here. By the way, lossy compression allows you to choose a quality of anywhere between 0 and 100%. User will not notice any differences, but we can save memory and draw image faster. An image that was 36 kilobyte size is become 25, which is a 30% reduction. While this might seem like a small memory savings for just a few images, it can become significant when dealing with millions or even billions of images. For example, a social network with such a large numbers of images will benefit from this optimization a lot. The choice between PNG and JPEG often depends on the complexity of the image. This picture shows two examples of the image that look very different depending on which compression algorithms is used. Image on the left has a lot of small details and compresses better with JPEG, while the image on the right has larger areas of the same color and compresses better with PNG. So if you need to preserve fine details and high resolution, choose PNG. If PNG is large color palette, choose PNG 24, otherwise PNG 8. It's general tips. Let's see iOS specific recommendations. Apple advises to use PNG format for images. Create images that don't need to be resizing and remove alpha channel from opaque PNG. Apple recommends that you use PNGs as graphics for your user interface because in building process, in an effort to improve the performance of drawing on iOS devices, those images get optimized by open source tool named PNG Crush. By the way, there is another useful setting for PNGs that can strip metadata from it. If you are uploading an image from your server, you can process them through PNG Crush on it. Optimization with PNG Crush process involves pre-multiplying the alpha channel and swapping the order of the RGBA channels to BG array. This corresponds to the internal format used by the graphic chips in the iPhones. For iPhone models 3 and later, it's recommended to use compressed PNG files as they are approximately twice as fast as compressed versions. Here are three main stages involved in rendering images in iOS. Time to allocate or initialize your image with data from disk. Time to decompress the compressed bits into an uncompressed format. And the time to transfer the uncompressed data to a CG context. This may include resizing, blending, and anti-aliasing. The compression takes up most of the time when rendering an image on the screen. I found a great article about the compression process in iOS with benchmarks that I would recommend you to check out. I will leave links to the materials I used to make this video in the description. PNGs are optimized for iOS use, but they may not be the best option for every situation. If you don't require a perfect pixel copy of your image, a perceptually optimized JPEG can be used. If you use tools like Image Optim to make your image smaller, compressed PNG file setting will undo all optimization work due to the image being rebuilt. You will have to choose whenever the image will be smaller or displayed faster. SVG provides a declarative way to describe vector graphics using XML. XML is a declarative markup language that is used to structure data. SVG uses XML to describe graphics elements and their properties using text such as circle, rect, and path, which define the geometry and style of the elements. And actually, you can embed a bitmap image in SVG. PostScript is a programming language that uses a procedural approach to describe pages and graphics. It contains commands and functions that describes how to output text, vector lines, curves, and image to a page. As in PostScript, vector graphics in PDF are constructed with paths. Paths are usually composed of lines and cubic Bezier curves, but also can be constructed from the outlines of text. PDF, as well as SVG, can contain bitmap image inside. Raster images in PDF, called XO objects, are represented by dictionaries with an associated stream. That dictionary describes the properties of the image, and the stream contains the image data. Although there is native support for SVG and PDF in iOS, you will not be able to download them from the internet and initialize your image with initial data. You can only use SVG or PDF from the bundle. Instead, you will need to use hacks such as WebView, third-party libraries like SVG-Kit, or Blackmagic, methods from private Apple frameworks. As for the differences between PDF and SVG, PDF has a lot more features than SVG. We don't need to go into details, but what we do need to know is how quickly each format renders and how much storage space it takes up. Let's look on the benchmarks. App size impact. We are interested in this point. PDF is much bigger than SVG, 45.5 against 18. And runtime performance impact. There is no measurable runtime performance difference between preserved vector data turned on and off when the image is drawn on a GTX size. However, drawing an image with preserved vector data enabled is much lower when the image is stretched. Stretched SVG images have a slightly better performance than the stretched PDF images. If you import an image from a Figma or Sketch, then pay attention to the image format. If you see a raster, then when importing, you will choose PDF or SVG, there will not be a vector image inside. Like I said before, the file format like PDF or SVG does not specify that there will be a vector image inside. I made a teeny command line tool that will run through your assets, look into PDFs and SVGs and tell you what's inside, a vector or a raster image. An interesting one, you can encrypt a message or another file into a bitmap image. This is called stenography. There were even exploits that placed an executable file in the image and it was executed when the image was opened. Have a look at this vulnerability in iOS related to the TIFF format. It could even be used for zero-click attacks. Let's figure out how to import vector images into a project. While you can simply move raster images into a project in 3 sizes, working with vector images is a bit more complicated. When a single-scale PDF or SVG image with preserve vector data option disabled is used for an image set, Xcode generates corresponding 1x, 2x, and 3x PNG image depending on the build target and build time. And at runtime, the application loads the PNG image from the app bundle, so the runtime behavior is the same as if PNG images are provided for the image set. When a single-scale PDF or SVG image with preserve vector data option enabled is used for an image set, Xcode adds the image vector data to the app bundle at build time. At runtime, if the image is drawn at different size from the intrinsic image size, the vector data will be used. Another plus to use vector is generating fewer assets, and automatic support for present and future display densities seems appealing and convenient. If Apple will make 4x density, for example. Now let's talk about asset catalogs. Asset catalogs provide a convenient way to structure and control your app's resources. In asset catalogs, each asset represents a single resource, such as image, color, or data file that your app loads during runtime. An asset includes one or more variations of that resource for different device specifications, such as platform, screen, size, resolution, appearance, and language. When you access a resource in your code, the system selects the appropriate variation to display based on the characteristics of the current device. just it. Simple. Here are some tips to work with assets catalog. Your asset catalogs can take minutes to compile on an initial build. If it gets really annoyed, separate your assets in a separate pre-built framework, so you won't need to build it every time. Asset catalogs allow Xcode and the App Store to optimize your app's assets with PNG Crash, for example, that is already familiar to us. Use asset catalogs instead of putting your assets in your app bundle directly. You can extract assets from iOS apps downloaded from App Store, and anybody can do it with your app too. So, if you store something sensitive in your asset catalog or bundle, don't do it. Don't store unnecessary resources. Delete them on time. It will be useful to know or remember about rendering mode. Template rendering mode will draw an image ignoring its color information, creating tintable images where a new color will paint over all non-transparent pixels. It won't work for a JPEG, as we remember there is no information about the transparency of the pixel, but it will work for vector images. In Asset Catalog, you can even add a resizable area to an image. Compression type. You can choose whatever you want for your images. And also, you can use on-demand resources in your app with help of Assets Catalog. We put our pictures in Assets Catalog and then what happens to them and where are they placed when we build the app? When you build a project, all your non-empty assets, .xassets, which are added to build phases copy bundle resources, will be compiled into assets.car. This file like archive, CAR format might stand for compiled asset record, which is generated by Xcode during building and set up by build settings asset catalog compiler. Actually, you can pull out the images from assets.car with different tools, but we are more interested in this command. Let's inspect what we got here. As we can see, when we add a vector and turn on the preserve vector, Xcode generates a 3x image and save it with a vector data. We can also open it through a hex reader. We see our vector image here. If you're interested in, I will leave a link to great explanation about the CIR file. Take an example. So you want to present this image. If you load full 2000 on 2000 pixel image directly into memory without unsampling and display it on a smaller container, you will run into two major issues. Memory overhead. Images are stored in compressed formats like JPEG or PNG, but when loaded into memory, they must be decompressed into a full-sized bitmap. Since iOS typically use 4 bytes per pixel, a 2000 on 2000 pixel image will take up 16 MB of RAM. If multiple large images are loaded simultaneously, memory usage can skyrocket, leading to performance issues or even app crashes. Performance impact. Displaying a high-resolution image inside a small UI container forces iOS to rescale it on the fly, which is pretty expensive job. This can slow down rendering, affecting the app's responsibilities and UI smoothness. So, how do we fix this? Before assigning an image to a UI image view, ask yourself, what size does it actually need to be on screen? For example, if your UI container is only 200 on 200 pixels, there is no reason to store a 2000 on 2000 image pixel in the memory. By downscaling the image from 2000 on 2000 pixel to 200 on 200, memory usage drops from 16 MB to just 0.16. 100 reduction. Ideally, you should store pre-resized images in your app assets or on server and download them at the required resolution. But if that's not possible, then we have to do it in runtime. You can resize images dynamically, synchronously using prepare thumbnail off, or asynchronously using prepare thumbnail with completion handler. For iOS 14 and below, use core graphics. With core graphics, image source create a thumbnail at index. If you move image processing of the main thread, create a separate thread or queue and handle resizing there. But before assigning the image to your image view, don't forget to switch back to the main thread. Another important point. Very often we need to display a large number of images in collection view, for example, and it will be a very bad idea to create a separate thread for each picture. This will cause a thread explosion. Therefore, do not create threads more than the cores of CPU. If you use GCD, it will resolve the thread explosion itself. There will be no more threads in the thread pool for the queue than the number of cores. Create a concurrent queue and asynchronously add image resizing work for each image in collection view cell with the user-initiated priority. If our picture doesn't need to be resized, then we still have something to improve. Before showing the image, it needs to be decoded. Again, if the picture is large and there are a lot of them, this is a lot of work. You need to take it out of the main thread. Use preparing for display method similar to the prepare thumbnail. A bit about a CA layer. It's important to know or remember that all of your images and views are baked by a CA layer, which is essentially a bitmap image of the rendered view object. CA layer has two additional properties that can improve performance. Should rasterize and draws asynchronously. Should rasterize is false by default. When set to true, the layer's contents only render once, which improves performance. It's cool for objects that animate around the screen but don't change in appearance. Draws asynchronously is the opposite of should rasterize, and it's also false by default. Set it to true to improve performance when the app needs to repeatedly redraw a layer's contents. This might happen, for example, when you work with an emitted layer that continuously renders animated particles. But don't use something just because it sounds good. Always test it and think about pros and cons of every approach. We don't often need to display a very large images. Most likely it will be images that you scroll and zoom. Maps, for example. To take the work of maps possible in iOS, we use CI tiled layer. CI tiled layer performs tiled rendering, allowing Apple Maps to handle infinitely large images by breaking them into small pieces, rendering and caching them as needed within the scroll view. Hey, it's me again. Actually, I'm editing this video right now and decided to record a small addition to cover a few important points. I mentioned that you can vectorize an image using AI, but you can also upscale it up to 16 times for free and locally using Upscale or Obsidian or consider SwiftGen for managing resources. Before each build, it scans your assets and automatically generates an enum with a static property for each image set, color set or data set in your catalog. This means that you can reference them as constants, improving type safety and eliminating string-based asset lookups. But SwiftGen isn't just for images. It also simplifies working with localized strings, fonts, and other resources. Video I only talked about SVG, PDF, PNG and JPEG, but of course iOS supports more than just this. I will leave this as homework for you. Research what other formats iOS can handle. HEIF, for example. If you want to dive deeper into UI and image handling, check out libraries like Y-Sync layers for efficient rendering and SVG-Kit, which I already mentioned for handling SVGs. Explore more WWDC talks, API for Apple's iOS frameworks and their documentation. The next level includes topics like OpenGL, Quartz, and understanding what hardware involved into graphics rendering and how iOS interacts with it. I never used to leave comments on videos. If I liked one, I just hit the like button. But once I started uploading my own videos, I finally understood why almost every YouTuber asks for comments. It's not just for promotion, for YouTube algorithms, it's for feedback. Was this video useful? Was it interesting? Did I miss anything or make a mistake? These are important questions for me, and your feedback will help improve future videos. So I'd really appreciate if you left a comment below. Goodbye.